The Lexicographic Trie compression system is a structured data organization framework designed for efficient prefix-based string storage and retrieval. This manual documents the complete internal architecture, configuration parameters, and operational characteristics of the system. The compression mechanism reduces memory overhead while maintaining logarithmic access patterns. All measurements are expressed in bytes unless otherwise noted. Default values are provided for each configurable parameter. Node structure definition begins with a 32-bit header field containing the node type identifier in bits 0 through 7, the child count in bits 8 through 15, and reserved padding in bits 16 through 31. Each node maintains an array of branch pointers allocated contiguously in memory. The character payload is stored separately in a shared string pool to reduce duplication. Leaf nodes contain a value reference pointer of 64 bits pointing to the associated data object. Compression occurs at the branching layer through suffix collapsing. When a node has only one child and the combined path length is below the compression threshold of 16 bytes, the nodes are merged. The compression ratio is calculated as the byte savings divided by original node size. A compression event triggers a memcpy operation with size parameter equal to the merged node byte length. This operation completes synchronously before returning control. String pool allocation follows a first-fit strategy with alignment boundaries at 8-byte intervals. The pool maintains a global free list sorted by address. Fragmentation is minimized through coalescing of adjacent free blocks whenever a deallocation event occurs. The pool size parameter is configurable from 256 kilobytes to 2 gigabytes. Initial allocation requests that exceed available contiguous space return a null pointer rather than blocking. Traversal operations proceed in depth first order by default. At each node, child branches are examined in lexicographic order. The branching factor ranges from 1 to 256 depending on the character set and compression state. Traversal time is proportional to the prefix length plus the logarithm of node fanout. Early termination occurs when null pointer is encountered or when the search string is exhausted. Insertion begins with a traversal operation to locate the appropriate parent node. If an exact match is found, the value pointer is updated in place. If the path does not exist, a new node is allocated and linked to the parent. The insertion cost is O of the prefix length in the common case. Node expansion occurs when the child count reaches a configurable threshold, defaulting to 128. Deletion operations mark nodes as inactive without releasing memory immediately. Batch deletion cycles run at configurable intervals, defaulting to once per hour. During a batch cycle, the system traverses the entire tree structure and reclaims nodes marked for deletion. Orphan string pool entries are identified through reference counting and returned to the free list. This deferred cleanup reduces contention in high-throughput scenarios. Memory usage accounting maintains separate counters for node allocation, string pool usage, and pointer overhead. The reported memory footprint includes all allocated blocks regardless of compression state. Peak memory tracking is maintained across the lifetime of the process. Memory statistics are accessible through a read-only configuration interface returning a structure containing the current allocation, peak usage, and fragmentation percentage. Bulk loading operations process input data in sorted order to minimize tree restructuring. The loader interface accepts an iterator of key-value pairs and builds the tree structure bottom-up, in single-pass execution. This approach reduces memory churn compared to individual insertion operations. The bulk loader is thread-safe when invoked with exclusive access to the tree structure. Return code indicates the number of successfully inserted entries. Prefix queries return an iterator that yields all entries with a given prefix in lexicographic order. The iterator maintains internal state, consisting of a node pointer and a position counter within the current child array. Iteration continues until a leaf node is reached or a branch changes the prefix away from the search string. Iterator invalidation occurs if the tree structure is modified by insertion or deletion during iteration. Range queries accept a lower bound and upper bound string parameter. The query engine locates the lower bound node through standard traversal, then continues iteration until the upper bound is exceeded. The iterator yields entries in sorted order between the specified boundaries inclusive. Range size estimation is provided through a separate cardinality interface returning an approximate count without full iteration. Snapshots are created through a serialization interface that outputs the complete tree structure in a binary format. The snapshot process acquires a reblock on the tree to ensure consistency. The output buffer receives sequential writes of node headers followed by string pool references. Snapshot size is proportional to the total number of entries plus the string pool size. Restoration from snapshot reverses this process through deserialization. Configuration parameters control compression threshold, node expansion size, and batch deletion interval. These parameters are set at initialization time and are read only thereafter. The compression threshold parameter influences memory utilization versus access performance trade-off. Decreasing the threshold reduces memory overhead but may degrade cache locality. The default parameter values are tuned for general workloads. Concurrent access is managed through reader-writer locking at the root node level. Multiple readers may access the tree simultaneously when no writer is active. Write operations block all other threads until completion. The lock implementation uses a spin lock for short critical sections and a condition variable for longer operations. Lock contention monitoring is available through Performance Instrumentation Interface. Error handling follows a return code convention, where 0 indicates success and non-zero values indicate specific failure conditions. Invalid pointer errors return code 1. Allocation failures return code 2. Lock acquisition timeout returns code 3. All error conditions are logged to a debug output stream before returning control to the caller. Performance characteristics indicate average, case insertion and lookup time of O of the prefix length plus logarithm of fanout. Memory usage is approximately 40 bytes per node plus string pool size. Under typical workloads with English language strings, compression reduces overhead by 30 to 40%. Batch operations at scale complete in linear time relative to entry count. This concludes the course system documentation.